Okay, I think folks are still filing in, but we'll go ahead and get started. So hello everyone, and welcome to the final press briefing of the now canceled, unfortunately, 239th meeting of the American Astronomical Society. You are in Intriguing Stars and Citizen Discoveries, and it's currently the 13th of January, Thursday at 2:15 p.m. Mountain Time. And we have got another full lineup for you in this final briefing. So my name is Susanna Kohler. I'm the AAS press officer, and I will be your MC for this session. And I am joined by Haley Wahl, who's the AAS Media Fellow and a graduate student at West Virginia University. Haley will be monitoring the Q&A session. And then Carrie Hensley is our AAS Deputy Press Officer, and she'll be putting out the press releases associated with this briefing. There should be around 4 of them, and we'll get those all out today. And she'll also be keeping an eye on the technical side of things. So the press kit at this point online is updated as through yesterday, and I will make sure that by the end of today, it contains all of the briefing videos from the entire week, all of the slides from the presentations, and the press releases. So that is your go-to one-stop shop for all of the materials associated with the briefings this week. And if this is your first time here, I'll go ahead and give a brief description of how this is going to work. So first off, note that we are live streaming this to YouTube. And the way that we'll do this is we will give a short introduction. I'll give a short introduction to everyone, and then we will go straight into the presentations back to back. And then at the end of that, we'll move into a Q&A session, at which point Haley will moderate that and we'll read out the questions that you've sent in. Ah, good, we got our presenter back, excellent.
Randomly crashed.
I'm glad you're back.
Thank you, so am I.
So if you have any questions, you can send them in via the Q&A box at the bottom of your screen. And we've asked our presenters not to answer those via writing during the presentations. We will get to them all out loud during the Q&A session at the end. Note that when you send in a question, you should indicate your name, your affiliation, and who the question is for. And also, if you see any questions that are especially interesting to you, you can upvote them, and we'll try to get to them in the order of priority. So without further ado, this final press conference is a little bit of a 2-part press conference. The first part, we're going to be looking at some really interesting results recently related to intriguing stars. So first off, Andrea Dupree will be presenting on Betelgeuse, the Great Dimming, before and after. Andrea is from Center for Astrophysics, Harvard and Smithsonian. And then we will have Scott Engle from Villanova University presenting on Living with a Red Dwarf, Improved Relationships for M Dwarfs. And then we'll move into the second part, which will have 3 briefings from 4 presenters, or 3 briefings from 3 presenters plus auxiliary, on some recent discoveries that have been made not only by professional scientists, but also by citizen scientists. So first we'll have Paul Dalba from the University of California, Riverside, present the discovery of a TESS giant planet on a 261-day orbit enabled by citizen science. Then Emma Softich from Arizona State University will present the discovery of the widest known brown dwarf binary. And she's got Adam Schneider on reserve to answer questions from the US Naval Observatory Flagstaff Station and George Mason University. And lastly, Nico Adams from University of Minnesota, Twin Cities will present Galaxy Zoo Clump Scout, surveying the local universe for giant star-forming clumps. So with that fantastic lineup set up, let's go ahead and get started. I will hand this over to Andrea.
Thank you, Susanna. Let me try to share my screen here, and we will see what happens. Yes, we'll see what happens. Here we go. Okay, I'm going to talk about Betelgeuse. Betelgeuse, you may know, is the bright star marking the shoulder of the Orion constellation. I'm talking about results from many, many colleagues and collaborators, which is why I have the picture of the crowd down there. We have a group called the Mob, where for months of Betelgeuse, we're all looking at it in various ways. So I just wanted to acknowledge that. Why do we care about Betelgeuse? It's large, it's bright, it's nearby, and it's unique because we can resolve the surface. It's only the sun is the only other star where we can clearly resolve the surface. And that means that we can obtain spectra and images of different parts of the star. And what we're interested in is how stars lose mass. And this way, we can observe it directly and directly find out, does it come from the poles? Does it come from the equators? How do stars lose mass? How does this supergiant lose mass? And mass loss, of course, affects many characteristics of stars. The evolution, the collapse. When it becomes a supernova, it will affect how the supernova light curve behaves, depending on how much material has been lost. It has a lot to do with the amount and the way in which stars lose mass. And we don't know how this happens. And of course, fingers crossed, we're looking at a star to see how will it behave before it explodes as a supernova. Let's move on to the next one. Let me remind you what happened that caused such great furor in the press and in the public. This is just a light curve. So it's a plot that shows you when the star is bright, it moves up to the top as a function of time. And you notice that up until this is perhaps the past decade, there's a very clear periodicity in the light curve. It's a 420-day period. It's nice and reliable. It's a fundamental period of pulsation of the star. Well, everything was fine until about December of 2019, when, I don't know if you can see my little arrow here, but at this point, it started getting dimmer. And that was a real crisis. It's a historic dimming. It went down to about 1.5 magnitudes, and it's the faintest it's been since it's been observed, which is over a century, 150 years ago. What's happened subsequently? Let's take a look. Let me just get rid of myself here. I've got pictures in the corner, which I don't want. Okay, it's not going away. I'm sorry.
We can't see it. Only you can see it.
Well,
so
I can see it, and I want to see what's going on.
Oh.
No, this is what this shows with the light curve subsequent to the Great Dimming. And what we've put on top of this is a little curve in broken black lines that indicates the 420-day pulsation that it has been reliably carrying out for the past 20, 30 decades. And you can see that after the Great Dimming, suddenly we are missing the pulsation. We're missing it. The whole character of the light variation has changed substantially. So something has happened. Actually, I have got a measurement from last night and some Hubble measurements 2 nights ago, and it may be coming back to its 420-day, but it seems to be turning up again, at least this past 2 nights. So clearly things are happening. Let me continue and give you what we now think is a picture of what went on. I'm going to take you as a function of time through the past year and a half. And we start out on the left when in January through March in 2019, optical spectra that were unresolved but analyzed with a very clever tomographic technique showed that shocks were developing in the deep photosphere and moving outwards through the surface of the star. Optical spectra were taken. In addition, imaging was taken. This is an image from the gravity and sphere at the ESO telescopes in Paranel, showing that the image of the star in optical light looked perfectly fine, looked normal. There was a bright spot. We know there are bright, large convective spots, and that looked fine. But underneath in the surface, we now know that material was moving out. As we move through to the fall of 2019, September through November, is when we had spatially resolved Hubble observations. And these Hubble spectra showed us that the chromosphere was moving out in the southern hemisphere of the star, that this photospheric outflow had moved out to the chromosphere. Remember, a supergiant is big. A supergiant is really big. And if you put Betelgeuse at the center of our solar system, it would extend out to Jupiter. So at 5 kilometers a second, it takes 5 or 6 months to get out to where the ultraviolet lines, emission lines, are formed. So in September and November, we saw the outflow, the signature of outflow and higher density material coming from the southern hemisphere. And then in January, February, when it became very, very dim, the surface gave cool measurements, cooler temperature measurements than we had seen before. And also when it was imaged in the optical, we could see that there was a dark shadow on the surface at the southern part of the star. So several things had happened that we could infer from the near infrared spectra that it was cooler, from the optical image that something was blocking the southern hemisphere of the star. And we think what's happened is that this is a surface mass ejection. And this is the first time that it's been observed directly. Now in the sun, we see coronal mass ejections. Those come from high temperature coronal regions. Betelgeuse doesn't have a high temperature coronal region, but we have seen something quite different. We've seen that the surface of the star was moving outwards, perhaps propelled by a magnetic field, assisted by the pulsations and the radial velocity, which was very extended and constant, moving out prior to the dimming. And we believe that this left us not only with a less dense atmosphere, but also a cooler stellar surface. And that this sort of episodic mass loss adds to the normal mass loss and can be quite substantial. So we're introducing a new term here, which we've been able to observe for the first time directly and follow it through the atmosphere, and that's a surface mass ejection. And I think that is the end. Thank you very much.
Okay, let's go ahead and launch right into our next one. Scott?
Let's see here. Is it sharing just fine?
Yes.
All right, perfect. All right, well, thank you very much for having me. Today we're going to talk about the Living with a Red Dwarf program I've been carrying out here at Villanova University with my colleague Ed Guinan for quite a number of years now, as it turns out. We'll get into to just why it's been taking so long. So, Living with a Red Dwarf program, we're talking about red dwarfs or main sequence M dwarfs or M-type stars. There's been a good bit of interest in them for a long time now. They're by far the most numerous type of star in our nearby stellar neighborhood when you count stars themselves, or if you count stars and substellar objects, brown dwarfs, or if you count white dwarfs, anything like that. M dwarfs outnumber them by a great deal, make up 75% or 78% or so of actual stars. When you bring into account brown dwarfs, white dwarfs, they still make up 55 to 60% of all of the objects. So their numbers alone make them very interesting. You want to know exactly how they work. Recent studies from the Kepler satellite, TESS satellite, statistical studies also indicate that they may form more planets on average than more massive, FGK type stars. So the stars themselves are fascinating because they're so numerous. You want to know how they operate, but also it may seem like they, on average, are more likely to host a planet, or they may host more planets than the other types of stars around us. So we want to know what's going on with M dwarfs, just overall. But it turns out they are difficult to understand. They're smaller than the sun in terms of their size, in terms of their mass. They're much, much lower luminosity. So they remain stable for a very long time. Because they have low masses, their cores are lower temperature, they burn their nuclear fuel much slower, they evolve much slower over time. So figuring out their bulk parameters, for the most part, is okay. Their ages are very difficult to determine. And age is one of the three key parameters of any star. If you know a star's mass, you know its composition, then you can, for the most part, depending on how accurate your model is, you can determine what it's going to do throughout its lifetime within certain uncertainty. But if you want to know what it's doing right now, then you need to know how old the star is. And that's where the difficulty comes in with M dwarfs, because they evolve so slowly. Some of our best methods and some of our standard methods, astroseismology, fitting an isochrone to a star, fitting its luminosity, its temperature, and applying an evolutionary track to it, these methods don't work for M dwarfs. Based on experiences with more massive stars, G-type stars primarily, we know that their magnetic activity, though, and some of these magnetic tracers, they do evolve at an appreciable rate as the stars age. Specifically, one of the observables, if you will, that we knew we could latch onto was the rotation rate of each star. So if we just stare at these stars for long enough, and if we can measure the rotation rates of them, then we would be able to put together a relationship of one of these indicators of magnetic activity over time. It works for rotation rates, it works for X-ray activity, ultraviolet activity, any of these things. Build up a relationship between the ages of these stars and one indicator or another of magnetic activity. Simple enough diagram of how it works. So we'll just use the case of spots on the surface of the star. Starting off on the left here, have a nice immaculate or pristine star. As it's spinning around and rotating, light curve will show next to nothing. If you have a nice favorable situation, one hemisphere has a spot, the other hemisphere has nothing. Spot rotates into view, the spot is dark, so your view of that star will show it dimming. When the spot rotates out of view, the star will brighten again. As you can see it rotating over and over, hopefully you'll see this happening periodically, and now you have the rotation rate of that star. Complications start to come in when there's spots on both hemispheres, light curve will go flat. Again, you can have uneven distribution of spots is all you want. One spot, two spots, perfect. See a rotation again. Heavily spotted versus unspotted, great. It'll be even dimmer on the one side. Heavily spotted on both sides, as long as it's uneven. That's all we want, so we can see some sort of variations. That's it. So it can take a while. It all depends. Sun, on average, depending on where you're looking at, 25 to 30 days or so for it to rotate. Fortunately, Villanova, we're part of a consortium with the 1.3 meter robotically controlled telescope at Kitt Peak National Observatory. So I have access to this telescope. I figured to just add a bunch of M dwarfs to the scope. Find some that are of known ages, because we're looking to calibrate this relationship in the first place. So that's where difficulty first popped up, but we were able to get around that relatively quickly. The problem for a long time was that young M dwarfs were easy enough to find. They're members of stellar clusters, stellar associations, are still gravitationally bound to each other, but they break up over time. We know of a couple clusters that exist up to 2 billion years old, 4 billion, maybe 6, arguably. But for the most part, they break up. The ones that we do know of that are fairly old are very far away, and these M dwarfs are dim. So it's very hard to get the type of data that we need in order to measure these rotations. At the very, very old age end of the relationship, you can find their ages from statistical relationships within what membership of the galaxy, what population of the galaxy they belong to. Based on how they're moving through the galaxy, they belong to either the thick disk of the galaxy, maybe the halo population of the galaxy. You can determine that they're out there 11 billion years old, 9.5 billion years old, somewhere. So at the very, very extreme range. It was in that middle point that we had difficulty. The solution came from finding not stars, M dwarfs that were bound to clusters, but that had single companions. They were gravitationally bound to simply one other star a common proper motion pair. They were just moving together throughout the galaxy. And that companion star was the type that could give you an age. It was either a more massive star, where you can get an age from one of these classical methods, or it was a white dwarf. And there have been a great deal of recent improvements in white dwarf models, initial to final mass relationship, just the synthetic models themselves. And we took great advantage of some of these. Just one came out just this past year, a big revamping of some of the white dwarf models. So we got vastly improved ages for the white dwarf companions. And that allowed us to fill in a lot of these middle ranges. So we had our M dwarfs with known ages from the companion stars that they were moving with, assume they formed at the same time, and just started staring at them with the telescope. You need long series of photometry. You want to measure the brightnesses of these stars for a long period of time, and you need that combination of precision as well. And the issue, I said, the sun take around a month or so for it to rotate. For the M dwarfs, it turned out it can take a very long time for them to rotate, depending on how old they are. And your observing season is only going to last a few months, maybe up to 4 to 5, maybe 6 months if you're very lucky. And it can take an M dwarf that long to rotate if they are very, very old. So within 1 year, maybe you will catch one single rotation if the spots are favorably positioned. So it's taken a very long time, especially for the older M dwarfs, which is the ones we're very interested in, or at least the middle ages up to the old one. So start off with obviously a favorable one. This is a press conference, so you want to show your successes. So every once in a while, you catch one that's really, really stable. And you see spots that just come back year after year, and you see rotation, 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 and it just keeps on happening. So that's great. And each one of these represents a year with the telescope. So you can see just how often we came back at it. And the telescope, you know, for the most part, years have been very good. And fortunately, the other members of the consortium, other members, astronomers at Western Kentucky University, South Carolina State in particular, they have done great deeds keeping the telescope operating. Because it's a robotically operated telescope, there's no one in there at all times. It simply does its thing automatically every night. And apparently being there in the mountains of Arizona, one of the big things we have to keep on worrying about is giant moths that work their way into the building. I guess they just live everywhere within the building, but they seem to really love getting into the optical path of the telescope itself. So you're going through images and all of a sudden you find the silhouette of a massive moth just landing on top of your star as you're trying to get data. And every once in a while, somebody has to go in there with a can of air and get out all the moths and everything. But fortunately, sometimes things really work out like this. It can take, 1, 2, 3, 4, 5, 6, 7, 8, 9, missing year here, 11 years that we've been observing this star. This has been very successful. Some of them were flatlined for some of those seasons. So you just have to wait a few years for spots to favorably line themselves up. But managed to do it, revamped all the white dwarf companion ages, reworked all of our rotation rates. And as it turned out, the M dwarfs separated themselves, which we had hints of a few years back. But with these newer white dwarf ages from the new models they released, we got an even better idea of how this separation occurs. So here we have what we call the early, the more massive M dwarfs. So M0 to M2. Rotation rates that we're able to get for them, what we call the late M dwarfs, but basically from M2.5 to M6.5. Later than M6, so less massive than M6, they don't seem to follow any sort of behavior there. They keep on spinning rapidly up to very, very late ages. So we've been fortunate that we're able to find a great deal of rotation rates. You can see coming down here, 169 days for it to complete one rotation, 159 days. So they can take a while to complete one rotation. But the relationships now that we've been able to put together. Rotation period on the y-axis, age in billions of years on the x-axis. The early M dwarfs, the late M dwarfs. And something that was already been hinted at for these mid to late M dwarfs, the young ages, they start to get all over the place. There's a great deal scattered. This has been known for several years because once you get to around, it's theorized M3, M3.5, the interior of these stars changes. So it's one of the interesting things now that we're looking to investigate now that we have these relationships really firmed up. A few years ago, this was behaving like a straight line. And the early M dwarfs, K dwarfs that are more massive than them, G dwarfs, they all behave in this power law relationship. And we were worried, we were concerned why it was a straight line, why they would behave so drastically differently. But with these new advances in the ages and all the reductions we did of our photometry, now they behave much like the more massive M dwarfs. So it's really made a large difference in our relationships. So they do behave similarly now, even though the more massive M dwarfs have interior structures, much like the sun does. They have partial convective zone. Hot material rises up like boiling water, pushes cold material out of the way, eventually loses its energy, and then it sinks back down where it heats up again. So just underneath their surface, it's convective. Deeper than that, nearer the core, it's radiative. These later M dwarfs, though, they are fully convective. Everything underneath the surface is completely convective. And that is supposed to change the way that their dynamos operate. But they clearly still have these magnetically driven winds. They're losing small amounts of their mass over time. As they do that, conservation of angular momentum causes their rotation rates to slow down before that mass is eventually lost forever out into space. So they still have this spin down effect. They still slow down their rotations over time, even though they've switched over to the fully convective regime. A recent paper that was just published last year theorized that the switchover between these dynamo mechanisms wouldn't occur around M3 to M35. It probably occurs somewhere around M2.1, M2.2. So that was really interesting for us to see, because that's exactly where we're seeing the split in our relationships. So that's something that we're looking forward to trying to investigate. So we have these new refined relationships for rotation versus age. We have 60, 70% of the stars out there now. As long as you stare at it long enough to get yourself a good rotation rate, we can get you pretty accurate age for that star. Here we see them in now log space. Instead of applying a power law to them, take the log and we switched it up. So if you're observing the rotation rate, which is the easier thing for everyone to observe, we can get you the age. Putting it in log space linearizes their behavior. And here we can see once again how long it takes for these less massive M dwarfs to settle onto this singular track. This point here for them represents the Praesepe and Hyades group, so about 625 million years. So you can see the more massive M dwarfs have already settled. Here are some very, very young clusters. But here we have Praesepe Hyades for them. They've already long since settled onto a single evolutionary track. The lower mass M dwarfs still haven't quite done it yet. It's theorized that is from the depths, their convection zone. Barnes had several papers about it, about this connections within these stars, trying to connect from the I sequence to the C sequence. There's a great deal of theory that goes into it. It's one of the next things we're looking to investigate. We're hoping this data will help to further inform some of those models. So rotation versus age, and next, especially particularly important for planets around M dwarfs. I said they're smaller, they're less luminous. So in order to be within the classical habitable zone of these stars, in order to be warm enough, you have to be very close to the stars. You need to be at Mercury's distance, closer. But they're just as magnetically active as the more massive stars, as K dwarfs, G dwarfs. So their X-ray activity, their ultraviolet activity is just as high. That becomes an issue. Ordinarily, X-ray and ultraviolet activity is just related to rotation rates because ages are very difficult to encounter. But when you find planets orbiting these stars, you would love to know how old the planets are as well. You'd love to know how long they've been orbiting these stars, whether the orbits can be stable or not, how long these planets have existed for, what type of radiative environments they're subjected to now, but also how long they've been subjected to that environment. Gives you a lot of good information. So taking our relationships, we can now take these X-ray relationships versus rotation and put them in age space. So some of the reliable calibrator stars that we have with known ages and their X-ray measures, and these large error bars. The issue with X-rays, there's There's no free lunch when it comes to any of these measures. You want the rotation rates, you have to stare at them for a long time because they can rotate very, very slowly. If you want to get a good measure of their X-ray activity, because they can have long-term cycles and they can have flares and they can have this and that, you usually have to measure them multiple times because these error bars here, they're not indicating any sort of uncertainty in one measurement. They're showing you that there could be an activity cycle going on. So usually multiple measures of the same target and where they can dance around. That's what's highlighted here, like for the same age range where those stars can all fall along. So usually they either require multiple measurements just to account for all the variations they can occur with, or how long it takes just to watch them undergo a single rotation. And you want to catch them rotating at least 2-3 times so you can be certain as to what the period is. And then moving on to the ultraviolet, the most dominant feature within ultraviolet wavelengths is the Lyman alpha line, around 1260 angstroms. It is also very, very difficult to model. There are several people actually doing very, very good work modeling it. The Muscles team is the first one that comes to mind. And they have released a good bit of measures. They found some high velocity stars. They have done some very good theoretical work removing some of the contamination, either from the ISM or geocoronal contamination that can really make it difficult to model that line in and of itself. But it makes up perhaps 80% of all the ultraviolet flux that these stars give off. So it's the one feature you really want to get a good measure of. So this is preliminary for now because their latest paper indicates that they might have to do a little more work in getting a pure, clean measure of Lyman alpha line itself. But again, tying in rotation, tying in X-ray and ultraviolet activity to better inform planetary habitability studies as well. Those are the relationships for the future. Always more data. Looking to add more and more rotation rates of known stars of known ages so we can further refine our relationships with the data that we have and tying into some of the all-sky surveys, looking to tie our rotation rates to long-term cycles like the one we know exists for the sun, and tying with some activity indicators, either from optical spectra, so the H-alpha line, calcium-2 line, some of these outer atmospheric indicators that aren't necessarily X-ray or ultraviolet. The little cartoon I had up there showing spots, that's very, very simple. The other thing you have to look out for is plages, bright spots that occur on these stars. They can also contribute to the variations as the stars rotate. If you ever look at solar dynamics observatory images of the sun, you'll see that it not only has spots, but it has a bunch of these ribbons going across it, these bright filaments as well. There are theories saying that at some mass range, M-dwarf rotation rates aren't spot-driven, they could be plage-driven. So perhaps from the HARPS data set or one of these planet hunting data sets that takes these spectra and has a lot of these activity indicators, I'd like to tie in with some of them and see if we can determine whether or not it really is spot-driven or plage-driven, comparing the two. And then so far, I have found some theories, some isochrones, some models that predict the more massive M-dwarfs and how their rotation rates evolve pretty well. It ties in well with our observations. I haven't found any to date that match up with the long rotation rates that we've found for the low mass M-dwarfs. So hopefully with this empirical data, the rotation rates that we've managed to measure, that'll better inform the models going forward and tie the theory and the observations in nicely. That is that. Thank you very much.
Thanks. Paul, if you want to go ahead and take over.
All right. Okay. All right, great. So once again, my name is Paul Dalba. I'm an NSF, Astronomy and Astrophysics postdoctoral fellow at the University of California in Riverside and Santa Cruz. And today we're going to be switching over to talking a little bit about exoplanets and citizen science. So let's get right into it. Okay, so when it comes to transiting exoplanets, like those that TESS is trying to discover, TESS being NASA's Transiting Exoplanet Survey satellite, the longer the orbit, the harder they are to detect. So I'm showing what an exoplanet transit looks like in this animation here on the left. And TESS produces literally millions of light curves. So astronomers typically look through this light curves with automatic detection algorithms. And when we search for transits, we rely on periodic transit events to identify these exoplanets reliably. The rule of thumb here is that we look for at least 3 repeating transits. And in this light curve data set I'm showing here, it's just an example of an exoplanet that transited every 6 days and showed reliably the same periodic transit signal over and over again. That's how we build up confidence that we're actually seeing a transit. But this introduces a little bit of a timing problem because the TESS spacecraft only observes most of the sky for about 28 days at a time. So as the length of orbits get longer, you push closer to the edge of that observational baseline that TESS is getting, and it sets a limit on the length of orbits that we can detect, at least in a periodic nature. If your exoplanet's orbit is too long, what you can end up with is a single transit event, which is what I'm showing here in this data set. And while this is pretty clear by eye, us looking at this light curve right there, it's actually like a needle in a haystack of spurious noise and other signals to an automated code. So it's difficult to identify single transit events automatically, and that's hard when you have millions of light curves to look through. Now, despite this challenge, we're actually really interested in single transit events because they are the best avenue to discovering cooler exoplanets, cooler being cool and also cool by temperature, that are on longer period orbits. And there's a lot of science motivation behind that. We can ask questions like, do short and long orbit exoplanets form differently or evolve differently? How do they change over time? What are the atmospheric processes going on? And what are the differences between short period planets that are very hot and longer ones that are cooler? But one of the big overarching motivations is that cool, longer orbit exoplanets are good stepping stones between the very, very hot Jupiters that we've heard about a lot in exoplanets, and then the very, very cold gas giants of our own solar system. So they're a very important piece of this puzzle. So that brings us to this particular cool giant exoplanet. I'll start by talking about the detection. So this was indeed a single transit event. I'm showing raw test data here in this particular light curve. And this was discovered by a citizen science group called the Visual Survey Group. This is just a group of amateurs that enjoy looking through exoplanet hunting data. They go all the way back to the Kepler mission, and they've become fairly sophisticated. They have their own set of tools that will display test data so that they can visually look at it and try to identify single transit events. And in the email that I received from this group in February of 2020, this was the quote, "Seems too good to be true." And this was the actual data set that they sent. And I agreed, it does seem too good to be true. It's a really glorious looking transit, and it's 24 hours long. A transit that long just screams long orbit, which is really, really exciting. So this is a detection that would have been very difficult to make with an automated routine, but the VSG Visual Survey Group got it. However, before we can celebrate and say, yes, we found a transit, we have to do some follow-up. And the follow-up that we did was with the Robotic Automated Planet Finder Telescope, which is at Lick Observatory. As a member of UC, I have access to this telescope. And we observed this for over 500 days in length to reveal the length of the orbit of this planet and the planet's mass. Now, the observation technique we were using here is called the wobble method, which is what's being shown in the animation, whereby you actually measure the wobble of the star that's induced by the gravitational pull of the planet. And in this data set I'm showing, you can actually see the data points wobbling back and forth and back and forth. We caught 2 full wobbles here with a little bit of data supplemented from Keck Observatory when there were wildfires at Lick Observatory. So this is the point in which we celebrated and said, yes, we have a really amazing new planet discovery. So just a little bit about the planet. This is a temperate Jovian planet. It's about the same size as Jupiter, but it's significantly more massive. It's almost 3 times the mass of Jupiter. It's about 170 degrees Fahrenheit in temperature, which is hot for us, but relative to other transiting giant planets, that's actually quite cold. And as far as other TESS discovered planets, this is the longest orbit planet so far. That's a title that it won't hold for long, but it has right now. Interestingly, models suggest that TOI 2180b is composed of over 100 Earth masses of material that's heavier than hydrogen and helium, things like rock and metals. And that's actually really interesting because we think there's a lot less than that in Jupiter and Saturn. And it might be pointing to differences in how this planet formed relative to Jupiter and Saturn. And the one main point I'll make is that TOI 2180b, this exoplanet, has a rare trifecta of properties that make it really exciting. It orbits a bright host star because it's relatively close. It has this long orbit of about 261 days, as indicated by that wobble data. And it also transits from our point of view. It crosses in front of its host star. There are many giant exoplanets that satisfy one or two of these, but it's very rare that we get all three. And it makes it a really exciting prospect for study, including future study from something like James Webb that could possibly do atmospheric characterization to really get at the interesting atmospheric chemistry processes that might be going on. And also just to be a little more speculative, I think this is an exciting prospect for the possibility of rings or exomoons, both of which have not been found outside of our solar system. I have no evidence to offer that those things actually do exist, but James Webb is the type of facility that could go about searching for them. So it's an exciting future to come for this one. But before we can do James Webb characterization, we have to observe a second transit. And so this motivated an effort. That's the last thing I'll talk about for this study. I'm showing again a subset of that wobble data that I showed before, highlighting when the planet was discovered. And we saw essentially one full wobble of the star. And so around the time here on the right where the arrows indicated, we thought, oh, hey, there's another transit coming. So the problem here was the TESS was no longer observing. So no one was looking at the star to see the second transit. So this kicked off a worldwide campaign to track down this second transit. The window of time we had to cover was 11 days, which was really challenging to do from the ground because the sun rises every day. So we had observers spanning 3 continents at 14 sites indicated here, several of which were citizen scientists again. So citizen scientists discovered the planet and followed it up. This campaign produced 55 data sets and over 20,000 individual images of TOI 2180, which was really exciting. I myself put on my citizen science hat and took 2 of these EV scopes out to Joshua Tree National Park for 5 nights to go after it. I won't say it now, but I have a fairly comical story of how I managed to upload the data from these things every day, which was challenging in the middle of the desert. Alas, at the end of this, we were left without a confident detection of the transit. However, we had many confident non-detections, and that allowed us to make a prediction. The TESS itself, by chance, is going to detect another transit of TOI 2180b in about 3 weeks from right now. And the VSG citizen scientists are poised to make that discovery as well. So there will be more news very soon from this system. So in summary, it was a citizen science discovery. We followed it up with the APF. It's a temperate Jovian planet with the trifecta of good properties. And there was a worldwide campaign to try to catch it. I just want to really quickly acknowledge all of the citizen scientists that made this work possible. They're listed here on the left, as well as the TESS survey that provided a lot of the observations. So thank you so much.
Great, thanks. Anna?
Well, hello, I'm Emma Softich. I'm an undergrad at Arizona State University, and I will be discussing the discovery of the widest known brown dwarf binary system. Just so everyone is aware, this work was sponsored by NASA and the National Science Foundation. So for this discovery, I worked with the Backyard World's Planet 9 Citizen Science Project, which is a collaborative effort between professional astronomers and citizen scientists from around the world. The main goal of the project is to identify previously unknown members of our solar neighborhood. This is done using NASA's Wide Field Infrared Survey Explorer, or WISE, which, as it's mentioned, takes images in the infrared, which is ideal for detecting brown dwarfs, where a brown dwarf is a substellar object in between stars and planets, normally too small to be considered a star, but too large to be considered a planet. And they're normally found by themselves in space. This figure here is an example of how we use WISE to detect brown dwarfs. You can see it is clearly moving with respect to the space in the background. So our discovery, CWISE J0146, was a brown dwarf candidate first submitted by Nikolai, Sam, Melina, Dan, and Frank, who are all citizen scientists. And here's a picture of it from our WISE image catalog. It's the very center and it appears to be moving ever so slightly. And according to the WISE images, it looks like just a normal L-type brown dwarf. When we look at JO146 in other higher resolution images, such as Vista Hemisphere Survey, Pan-STARRS, and the Dark Energy Survey, it is clearly resolvable into two objects. Brown dwarf binaries are quite rare, with a binary rate of approximately 10%, but wide pairs resolved in wide field imaging are even rarer still. There is only one similar system to this that has been found using this method. So in order to confirm that the two were moving together, we took measured positions from Pan-STARRS and DES through the Noir Lab source catalog. So that's what you see here in the figure. We have both components moving together through the time epochs. We then followed up with Keck NIRES spectra. You can see component A is on the top and B on the bottom. They are compared to L4 and L8 spectral standards following the Kirkpatrick 2005 publication. The spectra here is shown at full resolution, which is the gray lines, and smoothed to that of the spectral standards, which is the black, while our spectral standards is the red. All spectra has been normalized between 1.27 and 1.29 micrometers. And you will see the gaps in the spectra are at 1.4 and 1.9 are the water lines from Earth's atmosphere, and they were trimmed in order to better match the spectral standards. One fun thing to note on our B component, while the first peak, our J band matches the L8 spectral type, the H and K appear much bluer, which makes this system even more unique to have a blue brown dwarf component within it. So from our measured spectral types, we can estimate an effective temperature using empirical relations. And by combining that effective temperature with evolutionary models, we were able to find mass estimates for the components with component A at 72 plus or minus 6 Jupiter masses and 66 plus or minus 10 for component B. For the system as a whole, there is no measured distance, so we were able to also estimate that using empirical relations, coming up with a distance of 41 plus or minus 5 parsecs from us. Using the projected separation and estimated masses, we were also able to calculate a binding energy for the system. It's important to note that this binding energy is one of the lowest ever found for a brown dwarf pair. So our last figure here is separation versus total mass for all resolved binaries from the Faraday 2020 survey, where each component has a mass of less than 0.075 solar masses. The field age pairs are represented with the blue circles, while our young binaries are the gray squares. The dotted and solid lines show the instability regions as defined in the CLOSE 2007 publication, with the dotted lines representing the maximum bound separations for clusters on the left and fields on the right due to diffusion, and the solid lines representing maximum separation due to close catastrophic encounters. So you'll see that our object in the red isn't the widest because there's a few wider young brown dwarf pairs, but we do not believe that they will survive to meet field age requirements due to interactions with other stars. And now that we have JO146, we now have an example of a wide field age, that is to say not young but not old, brown dwarf that has survived its birth environment, which is very unique. You'll notice there is one other object that appears to be wider separated than ours. This is Widest 2150. It's another backyard worlds discovery. However, the primary in that system is an L1 and therefore likely considered to be a star and not a brown dwarf, but we have included it in our plot, seeing as it's right along the boundary. So that went a little fast, sorry. But this, our system, JO146, is very interesting because it is the widest brown dwarf pair we've found to date. And this brings up many questions, such as, is it truly one of a kind? Or is it just the first of its kind? Is there a whole population of these wide separated brown dwarfs out there just waiting to be discovered? And we can start to answer these questions by looking back at previously confirmed brown dwarfs and check again to see if there was a companion that we missed, or like we did in this instance, taking a second look at candidates that are submitted in the future. So I thank you for your time.
Thanks, Emma. And last up, we've got Nico.
All right, am I coming through?
You are.
Thank you. Yeah, thank you, Emma, for the presentation and all of our past speakers. I will also be talking about a Zooniverse project today. So to briefly introduce myself, my name is Dominik Adams. I'm a PhD student at the Minnesota Institute for Astrophysics. And what I'm presenting about today is the first science result from the citizen science project Galaxy Zoo Clump Scout. This is the first public announcement of our findings. And for those interested, our paper will be released on arXiv early next week. Now, before I begin, I need to acknowledge the support of NASA and the National Science Foundation, thank all of my collaborators, and extend a huge thank you to the more than 14,000 volunteers who took part in this project. If any of you happen to be tuning in, your work made this science possible, and we are very grateful for it. So briefly, the result we'll be talking about is that we have found a dramatic reduction in the number of giant clumps in modern galaxies compared to those in the early universe, and that this says some really interesting things about how galaxies evolve. So to start, there we go. If you examine galaxies in the modern universe, the last billion years or so of cosmic time, they tend to take on one of a few simple shapes. They can be ellipticals, which are basically just round blobs of stars, or they can be spirals of a few different types. And these have the very photogenic spiral arms that we're all very familiar with. And with a few exceptions, these shapes describe most of the galaxies we see today quite well. Well, compare this to the galaxies we see in the much earlier universe. So importantly, because light takes time to travel, the information from galaxies a few billion light years away takes a few billion years to reach us. So when we talk about the distant universe, we are also talking about the early universe. We're seeing snapshots of galaxies as they were much closer to when they were born. And if we look at deep sky images like the Hubble Ultra Deep Field, pictured here, we see that many of these very distant, very early galaxies are not well described by simple labels like spiral or elliptical. They are more complex. And one of the reasons is that many of them have these huge blue blobs that dominate their structure. In fact, within these blobs, gas is collapsing to form new stars about 10 to 100 times faster than the area around them. So these blobs are what we call giant star-forming clumps. Now, we're still learning about the properties of these clumps, and one mystery is exactly how most of them form. We think that it happens in one of two ways. First, galaxies that are especially chaotic and turbulent may form clumps in situ, in place, when huge pockets of gas condense and collapse under their own gravity. And ultimately, a clump could begin its life outside of the galaxy, ex situ, as a small independent galaxy, with its own properties and its own independent life, before being swallowed up by a much larger host in what's known as a minor merger. And we expect that clumps formed in situ and ex situ ways would have very different properties and would impact their host galaxies in distinct ways. So an outstanding mystery about the evolution of galaxies is where most of these clumps are coming from. Well, one way to address this question is by tracing the frequency of clumps over cosmic time and comparing this to other cosmic trends, such as how turbulent galaxies are over time or how often minor mergers are taking place. And generally, the way we trace galaxy clumpiness is by using something called the clumpy fraction, which is the number of star-forming galaxies with clumps divided by the total number of star-forming galaxies at a given time. This quantity is very simple to compute, and it allows us to compare how frequently clumps are forming in galaxies across very different eras of the universe's history. So what's plotted here are some existing measurements, not ours, but existing ones, of the clumpy galaxy fraction over time, where the red curve traces large Milky Way-sized galaxies, and the blue traces much lower mass galaxies, about the size of the Large Magellanic Cloud. Unfortunately, until now, there have been few to no measurements of the clumpy fraction beyond about 5 billion years ago. And this is because most large-scale studies of clumps focus on the distant early universe where clumps were first discovered. So our aim was to extend these curves into the modern universe and to fill in the final billion years of the clumpy fraction. And that is where our citizen science project comes in. So we launched the Galaxy Zoo Clump Scout project back in 2019, and our goal was to have volunteers examine about 60,000 nearby galaxies imaged by the Sloan Digital Sky Survey. This was the first systematic survey of the local universe for clumps ever conducted, and volunteers' job was to simply click on any bright blue off-center region in each galaxy. That's a task that's tricky for a computer, but very simple for the human eye. Each image was examined by 20 volunteers, and we combined the marks of those 20 volunteers into a consensus for each image. This was a complicated process, and we did this using a novel algorithm that will soon be getting its own paper. This was designed from the ground up specifically for citizen science, and it accounts for things for the first time, like the difficulty of each image and even the tendencies of each volunteer, whether they tend to be more reserved or more optimistic with how they mark clumps. Our volunteers finished this project last year, and here is a preview of the result. In total, our volunteers have found more than 7,000 galaxies containing more than 10,000 clumps spread all across the Sloan Digital Sky Survey. This is by far the largest catalog of nearby clumps created to date, and it's even more unique because each galaxy has been examined directly by many human eyes. So using this catalog, we finally have the statistical power to answer some of our questions. So let's return to that question at the very beginning. How does the clumpy fraction look in modern galaxies compared to early galaxies? What we see so far is that large Milky Way-sized galaxies are shedding clumps much faster than their smaller counterparts. That's the early universe. Let's add the modern update. And here is our main result. Only 2 to 3% of modern star-forming galaxies have giant clumps, which is about a 20 times reduction from 8 to 10 billion years ago. You can see how dramatic it is just by comparing the levels on this plot. What's more, this change has occurred not just for one type of galaxy, but for all of them of widely different masses, affecting both small and large galaxies alike. So with this result in hand, let's see what we can learn about why these clumps are forming in the first place. Remember that clumps can form from inside a galaxy due to internal turbulence, or from outside due to minor mergers. Now, according to observations, we think that the minor merger rate stays relatively flat as time goes on. And what's interesting about that, it is not consistent with a 95% or a factor of 20 drop in clumpiness over the last few billion years. On the other hand, we can look at how many galaxies show turbulence over time. And the trend we see there is much more promising. Galaxy turbulence does tend to fall with time. And what's more, it even obeys the same trend in galaxy masses as the clumpy fraction does, with the largest galaxies calming down much faster than their smaller counterparts. So, while we can't say anything for sure, our result definitely points to the idea that clumps are mostly forming in situ, or within the galaxies themselves, throughout cosmic time. And that means that the loss in clumps over time would be explained by the fact that galaxies are calming down and becoming less turbulent as they age. Now, to briefly wrap up, I'd like to emphasize that there is much more that can be done with this catalog. Because the clumps that our citizen scientists found are so nearby, telescopes can examine them in much sharper resolution than those found in early distant universe galaxies. And while we haven't taken high resolution follow-up of most of these galaxies yet, we can see a small preview of what this will look like by examining Hubble telescope images of galaxies on the right and seeing how much sharper they are compared to what we currently have from the Sloan Digital Sky Survey. As a reminder, this paper, along with a catalog of clumps, will be available beginning early next week. And I'm more than happy to respond to any questions sent to my email provided below. I'd like to thank AAS for going ahead with this press conference in the face of, frankly, extreme adversity this year, and all of you for your time. Thank you.
Thank you so much, everyone. There we go. Okay. So we are running just a little bit over time, but we will go ahead. If it's okay with all of you, maybe we'll extend this by about 10 minutes to make sure that we can at least get to some of the questions on the list. Great. Haley, why don't you take it away?
Thank you. Okay, our first question comes from Rick Feinberg of the AAS for Andrea. What's the connection between the ejection of mass from Betelgeuse's surface and the change in the star's pulsation period? Is the former just obscuring the latter? And we'll see the latter once the dust clears away?
No, it's really changing, and the dust is not clear, is not hiding anything that's going on, because the radial velocity is also unusual. We've never seen this phenomenon before. In other words, there's almost as much mass came out during this surface mass ejection as the star loses in a whole year. And so it lost a huge hunk of its atmosphere, became less dense, became cooler, and clearly had an effect on the surface pulsation. It's not being hidden by the dust cloud that's out there because the radial velocity is also anomalous. In other words, the period changed from 400 days. The last two periods have been 250 days. And we need a theorist, and it's not being hidden, it's really happening, and we haven't seen it before. So this is uncharted waters or atmospheres.
Very cool. Thank you. The next question is to Scott from Bill Waller of the Galactic Inquirer. Is there any data on X-ray emission variability from these stars?
And unless I'm mistaken, that one, he put in another question afterwards saying it was answered, because then my plot came up in a following slide.
Oh, sorry. That was further down the list.
because my Zoom crashed, I can't see all the questions anymore. I just see them now as they kind of come up. But I thought I read that it was answered afterwards.
Gotcha. Sorry about that. Okay, our next question is from Martin Ratcliffe, freelance for Paul. Forgive me if you mentioned this, but what is the magnitude of the parent star of TIO 2180b? And does it have another more well-known designation? If easily detectable in a small unistellar scope, it should be well within the range of many variable star observers. So for potential observers in the next 3 weeks, what magnitude dip is expected?
Yep, thank you. Okay, so the host star magnitude is 9.2 in visual band magnitude. So that's pretty bright when it comes to other TESS stars. And the dip in brightness that we expect for the transit is about 0.5%. It's actually a little under 0.5%, 0.4%, which is around 4 millimagnitudes if you're working in that scale. So what I'll say with the EV scopes, that's sort of right at the limit of what they're able to achieve under good conditions. And so it's exciting that I got it there, but you're absolutely right that other small amateur telescopes can certainly get that kind of a detection. So if you're able to achieve 4 millimag, then you can catch it there. And the other designation, it does have an HD number. It's HD 238894.
Great, thank you. The next one is for Emma from Monica Young of Sky and Telescope. Given that the brown dwarf pair's binding energy is so low, can you make a prediction for how long they might stick together?
That's a very good question. Sorry, turning blue from my background. That's actually one of the things that makes our system so interesting, is because the current models don't really explain how it has lived this long with such a low binding energy. I'm assuming there is a way that we can go about calculating how much longer they could theoretically stay together. We have not done that as of yet, but we are working on a paper on this discovery at the moment, and we might need to look into including that.
Great, thank you.
Yeah, one thing I'll just add real quick, that even though it has a low binding energy, it's quite stable. So we expect it to live for several more gigayears as it is. It's just the fact that it survived its birth environment, because it was born probably in a cluster, as most stars and brown dwarfs are, where it's much more dense. But now that it's out in the field and it's survived till now, it's not in a dense field anymore. So we expect it to live as long as it wants.
Great, thanks. It's a really cool system. So the next one is from Lisa Grossman from Science News for Scott. There's been some question about whether the age rotation rate relationship holds past middle age for sun-like stars. Do M dwarfs show rotation breaking at some point too? Are they too long-lived to tell?
For what we've seen so far, they seem to, at both the higher mass M dwarfs and the lower mass M dwarfs, they seem to show smooth relationships throughout the age range. Obviously, once again, for the lower mass M dwarfs, when they're very, very young, they're scattered all over the place. But intermediate to older ages, it seems to be a smooth progression.
Great, thank you. The next question is for Andrea from Dustin Rays. Any predictions or thoughts on near future evolution of Betelgeuse based on the SME findings? Also love the term SME.
Oh, yeah, I know. Well, we were going to call it photospheric mass ejection, and thought, well, photosphere is kind of a hard concept to understand, so we thought surface. Well, this is the first time we've seen this. We know, though, it's probably happened before, and because all of these stars, Betelgeuse, other supergiants like the hypergiant VY Canis Majoris, they have clumps of material around them. So clearly these have been ejected from the star. Not clear whether they all come from the surface of the star or whether they're more like coronal mass ejections. So we're going to keep looking. Maybe we'll find more.
Great, thank you. So the next one is from Rick Feinberg of the AAS for Paul. How bright is your new exoplanet's host star? Do you think everyone missed the second transit because the star is too faint for a good light curve from modest ground-based telescopes? Or perhaps because the orbital period isn't constant due to the gravitational influence of other planets in the system? I guess we'll know the answer for sure if/when TESS captures the next transit in a few weeks.
Yeah, thank you. We were observing at the time the transit probably occurred. I think the difficulty here was that because that decrease in light, the transit depth is only about 0.4%, I think it pushed the limits of the precision of what most of the ground-based facilities that we use could achieve. So I bet it's in the data, but we're just not confident enough to say that it's there. We'll be able to go back once we see the next one if TESS catches it. As far as other objects in the system, there is indeed one other object in this planetary system. In that radial velocity wobble data that I showed, in addition to the back and forth wobble of this planet, there's a long-term drift that indicates that there's a very massive object, whether another giant planet or perhaps a substellar companion, something else in the system that we haven't quite resolved yet. Now, whether or not that's interacting with our giant planet, we don't know. We'll need to get 2 more transits to be able to tell, but we'll have some idea once we do catch one more in February.
So cool. I will definitely be looking out for that. The next one is from Bill Waller of the Galactic Inquirer to Scott. How do your measurements of activity map to the M_E classifications?
So I assume talking about a DM versus DME classifications. So off the top of my head, I haven't, first of all, the short answer is I haven't investigated directly yet. Off the top of my head, the DME stars usually are characterized by a larger percentage of their surface area having active regions, particularly in the X-ray. So I would predict that they would be the faster rotators, the younger, the more active stars. Typically, that's where the E comes from, their higher emission rates. And if they're covered in active regions, they're usually closer to saturation in their magnetic fields. So I would expect them to be the active, younger M dwarfs. Now, whether or not there's a larger percentage of them in either the mass bins with the earlier or the mid to late M dwarfs, that'd be interesting to look into, definitely.
Great, thank you. Another question for Scott from Rick Feinberg of the AAS. Could you please show the X-ray plot again and clarify which symbols refer to the M0 to M2 stars and which symbols refer to the M2+5 stars? There seem to be more than 2 colors and shapes of data points. Thank you.
Yeah. Yeah, the reason there's 3 colors, the green was simply to signify that those are the stars that we have, or at least on the early age range, it's a group, a cluster that we have a bunch of X-ray measurements within. At the last 2 bins, those are those galactic populations that we have a bunch of X-ray measures within, just to show you some of the crazy X-ray variations that can go on within a single age range. And then within the mid ranges, those are single targets that we have known ages for thanks to their companion stars. So outside of the green targets, then the yellow is the early M dwarfs, the red is the mid to late M dwarfs.
Great, thank you. And the last question is for Paul from Lucy Fortson. Do you happen to know if TIO 2180b was also presented on the TESS Zooniverse project? And if so, why it might have been missed there?
So yes, it was. And the TESS Zooniverse project and the TESS Planet Hunters group did in fact detect this one. The timeline here is actually a little interesting to consider. So TESS observed the system initially, I think in December and January of 2019. And the data hit the ground at the end of January, and the VSG group that I was working with found it immediately right at the beginning of February. This was followed up by the second detection in the TESS data by the Planet Hunters group, and that was in May. And then the TOI, the TESS team, the science team, made the detection in August. So they did in fact find it. This is one that's been found by multiple people, including the TESS team. And it's fun to know because this is not the kind of thing the TESS team is interested in finding at all. This isn't the goal of the TESS mission, which is to find small planets on close-in orbits. This is very different than that. So it's not what TESS is looking for, but with the help of citizen scientists, the VSG group, the Zooniverse group, Planet Hunters, we can actually have a lot more science output from TESS in the long run.
Great, thank you so much. So that's all the questions that we have here. So I will hand it back to Susanna.
Wonderful. Thank you all so much for staying a bit longer to get to all of those. And thanks to all of our presenters, both in this session and this past week, for all of their incredible presentations, really great science. This was a lot of fun. Thanks to all of the public information officers who helped make this happen, supported their scientists, wrote press releases on very short deadlines. So much appreciated. And thanks to USRA for sponsoring this press conference, and to my fantastic co-hosts, Carrie, Haley, and Macy wasn't able to make it for this one, but Macy as well, for making this week run so smoothly. And I would be remiss if I didn't also say thank you to Rick Feinberg, former AAS press officer, who, while his face is not on screen with us right now, has answered all of my questions over the last several months, despite the fact that he was on vacation abroad and retired. So really appreciate that. And lastly, of course, thank you so much to all of you who are here watching and who have been watching all week and participating and asking fantastic questions and writing great stories. Really appreciate you being here. So I think all that is left is to have Carrie put up the final slide. Dun, dun, dun. I don't have it animated the way that Rick normally does. It's okay while Carrie tries to find it. There we go, yes. I truly, truly hope to see all of you in person safely for the June meeting, the 240th AAS meeting in Pasadena, California. That will be the 12th through the 16th of June. And I really think it's going to be an incredible, vibrant meeting, making up for all the lost time. So I really hope we'll be able to see all of you there in person. Thank you so much.